ख्याल से इंस्ट्रक्शन के बाद से नहीं हो रही।
अब पता नहीं, मुझे तो याद ही नहीं आ रहा। अब मेरे ख्याल से आज अभी स्टार्ट हुई है। ऑलराइट, सो आई थिंक रिकॉर्डिंग हैज स्टार्टेड. Do you want me to repeat the previous part or should we go ahead? Thank you, madam, for pointing. Is it okay? So we can move forward?
Yes, sir.
Thank you. Acha, I hope you can all hear the power supply anyway. All right. Acha, so we were discussing, yes, okay. I was just explaining the basic transition from antipodal to orthogonal, from single dimension to dual dimension. Remember, acha, you know, there's no problem to represent this type of signaling, especially when you know that they are y vector, as we saw earlier. Yes, it is y1 and y2, but we saw that y1 and y2, they were independent. So I can write this joint distribution y1 and y2 given S1 as product of individual, or you can say marginal densities y1 given times f of y2 given S1. Right? So very easily, so no need to worry. Okay, and again, remember, Hari Salman sir, in your previous course, maybe in probability or in linear systems, or I think probability or linear algebra, have you studied two-dimensional probability functions or multi-dimensional probability functions? Because
sir, joint
two-dimensional, so just
जॉइंट पीडीएफ पढ़ी थी एक्स वाई की, मतलब कि जो जॉइंट पीडीएफ है तो वो उनको
वो तो आप
देखा था।
अगर वेक्टर फॉर्म में आपने देखा था उसको? जैसे अभी तो हम
नहीं सर, वेक्टर्स नहीं देखे। नहीं सर, स्केलर्स ही किए थे, वेक्टर्स नहीं किए थे।
चलो ठीक है, तो यहाँ पे देखिए ना, थोड़ा सा हमें हो गया कि ठीक है जी, वेक्टर थे, मगर वेक्टर को हमने फाइनली एक तरह से प्रोडक्ट ऑफ टू स्केलर्स बना दिया, ठीक है ना? सो देन you come back to square one. So remember, this is also a full-fledged for multi-dimensional probability functions. Again, remember that it is also you know, from 0 to 1 probabilities, even for multi-dimensional. What happens in multi-dimensional representation, that your space is now multi-dimensional. It is not single dimensional. So your probability function is not on a single line, rather it is on a two-dimensional line. If it is a two-dimensional, if it, let us say, it is four-dimensional.
सर ये ज्वाइंट पीडीएफ ही नहीं है, मतलब कि ये ज्वाइंट पीडीएफ ही नहीं होगी, मतलब कि अगर ये वेक्टर की जो टू डायमेंशनल वेक्टर है, तो क्या ये वो सिंपल टू डायमेंशनल ज्वाइंट पीडीएफ ही नहीं होगी, इसकी जो पीडीएफ होगी, या डिफरेंट होती है वो ये चीज क्या पढ़ा रहे हैं अभी?
जी नहीं, मतलब देखिए ना, ज्वाइंट डिस्ट्रीब्यूशंस are not necessary that they are also in vector form. ठीक है ना? मैं ऐसे कहता हूँ कि जी I have 3 random variables, let us say 4 random variables. हमने थोड़ा सा शायद हमने वो चैप्टर 5 में मैंने शायद आपको रिवाइज भी करवाया होगा, प्रोबेबिलिटीज जब पढ़ा रहे थे, थोड़ा सा मैं शायद आपको रिवाइज करवाया था। वो जो ज्वाइंट गॉसियन डिस्ट्रीब्यूशन होती है, वो मैंने दिखाई थी आपको वहाँ उसमें चैप्टर 5 में।
सर उसका एक्सप्रेशन दिखाया था आपने?
हाँ, तो वो अगर आप उसको देखें ना, वहाँ तो उसने कुछ वेक्टर का तो कोई नहीं तस्करा किया हुआ। वो तो कह रहे हैं भाई 2 होंगे तो 2 की ज्वाइंट डिस्ट्रीब्यूशन की क्या सूरत हो सकती है, 3 की क्या हो सकती है, 4 की क्या हो सकती है। वो तो सिंपल
लेकिन सर ये मल्टी डायमेंशनल नहीं होगी ना, लेकिन ज्वाइंट पीडीएफ होगी तो मल्टी डायमेंशनल ना, मतलब कि आपकी जो फिर इनपुट स्पेस है वो सिंगल डायमेंशनल में तो नहीं होगी, जो इनपुट में दो रैंडम वेरिएबल्स आएंगे, तो ये भी मल्टी डायमेंशनल नहीं हो जाएगी ज्वाइंट पीडीएफ हमेशा?
वो बिल्कुल हो सकती है अगर आप उसको एक्सप्रेस इस तरह से करें। मतलब अगर आप सिर्फ ये कहें कि मैं तो सिर्फ मेरे 3 रैंडम वेरिएबल्स हैं और उसकी डिस्ट्रीब्यूशन को मैं देखना चाहता हूँ, तो अगर हाँ वैसे अगर आप उसको देखेंगे तो 3 डायमेंशनल, यानी कि वो जाहिर है x1, x2 और x3 में स्प्रेडेड होगी। सही कह रहे हैं आप, तो 3 वेक्टर्स में रिप्रेजेंटेड होगी। मगर वहाँ पे हम जब एज अ प्रोबेबिलिस्टिकली पढ़ाते हैं तो हम बिल्कुल सही कहने की डिस्ट्रीब्यूशन तो 3 डायमेंशंस पे होगी, मगर उसको फिर भी हम एज अ वेक्टर रिप्रेजेंट नहीं कर रहे होते, हम बस कह लेंगे हाँ जी 3 डायमेंशनल है या 4 डायमेंशनल है या 5 डायमेंशनल, क्योंकि ज़ाहिर है 4 या 5 रैंडम वेरिएबल्स पे डिपेंडेंट होगी। तो आप उसको कह सकते हैं कि जी वो मतलब 4 रैंडम वेरिएबल्स पे स्प्रेडेड है, मगर इसमें ये भी ज़रूरी नहीं है कि वो 2 रैंडम वेरिएबल्स आपस में ऑर्थोगोनल हों। और जैसे हम एक्स वाई जी एक्सिस पे अगर तस्वीर कर लें, ठीक है, वो तो कोई भी रैंडम वेरिएबल है, उनकी जॉइंट डिस्ट्रीब्यूशन है। मतलब वो ये मतलब है उसका कि कोई पॉइंट आप ले लें जो मसलन चारों रैंडम वेरिएबल्स की किसी की वैल्यू, मतलब आपके पास x1 x2 x3 x4 है, तो आपने उनमें से कोई वैल्यू ले ली, फर्स्ट के एक का 1 लिया, एक का 0.5 ले लिया, एक का 2 लिया, एक का 3, एक का 4, तो ये 4 वैल्यू। अब इस 4 वैल्यू पे आपकी जॉइंट डिस्ट्रीब्यूशन की क्या प्रोबेबिलिटी है, तो वो प्रोबेबिलिटी आपको नजर आ जाएगी। जॉइंट डिस्ट्रीब्यूशन का सिर्फ यही काम है कि वो आपको जॉइंट दिखा रही है उन 4 रैंडम वेरिएबल्स। अब इसमें ये कोई शर्त नहीं है कि वो रैंडम वेरिएबल्स आपस में ऑर्थोगोनल हैं, आपस में ऑर्थोनॉर्मल हैं, और वो आपस में अगर उनको विजुलाइज करें तो वो वाकईतन एक ऑर्थोगोनल सब स्पेस बना के आपस में 4 90 डिग्रीज पे होंगे। वो तो डिपेंड करेगा, अगर तो ये तो ना चारों के चारों आपस में जैसे अनकोरिलेटेड हों और सारा कुछ है, फिर तो आप उसको 4 डायमेंशनल में ऑर्थोगोनल स्पेस में विजुलाइज कर सकते हैं। वैसे वो ज़रूरी नहीं है, ठीक है, वो सिर्फ और सिर्फ एक फंक्शन है 4 रैंडम वेरिएबल्स का, मगर उसकी विजुलाइजेशन ऑर्थोगोनल वेक्टर्स पे नहीं आप कर सकते। हाँ ये सलमान साहब, थोड़ा समझ आ रहा है आपको? मैं फर्क समझना चाह रहा हूँ वेक्टर का और एक सिंपल जॉइंट डिस्ट्रीब्यूशन का। जब आप वेक्टर
सही
फॉर्म
है
में
सर।
कहेंगे तो वेक्टर फॉर्म में आपके पास जो, अगर ये फर्स्ट करें y1 y2 है, तो वो फिर ये हमें इसका बिल्कुल आइडिया है कि हमारी जो ज़ाहिर है n1 n2 की वजह से ये आपस में ऑर्थोगोनल हो चुकी हैं आउटपुट्स, ठीक है। तो ये इनको मैं अपने साई1 साई2 कह लें, इस स्पेस में मैं इनको एक मतलब कि एक वेक्टर फॉर्म या एक ऑर्थोनॉर्मल सब स्पेस पे मैं इनको विजुलाइज कर रहा हूँ इस डिस्ट्रीब्यूशन को।
सही है सर, ठीक है।
ठीक है, ये थोड़ा सा फ़र्क है, बस विजुलाइजेशन का फ़र्क है। और हमें फ़ायदा है अगर हम वेक्टर फॉर्म में कर रहे हैं, फ़ायदा हो गया कि हमारे पास डिस्ट्रीब्यूशन प्रोडक्ट्स हैं, वरना अगर जॉइंट में लेते तो जॉइंट में तो हम मारे जाते। आपको उनका कोवेरियंस भी चाहिए था, आपको उनका कोरिलेशन चाहिए था, वो कहाँ से आप निकालते फिरते। यहाँ जॉइंट है, सिंपल उनका प्रोडक्ट है, आपके पास डिस्ट्रीब्यूशन भी आ जाएगी बड़े आराम से उनके प्रोडक्ट से, और आपके पास हर पॉइंट आइडेंटिफाई हो जाएगा, हर पॉइंट एक ऑर्थोगोनल सब स्पेस। यानी यहाँ पे तो आपके कोर्स में इस वक्त तो हम 2 डायमेंशनली पढ़ रहे हैं, तो एक 2 डायमेंशनल स्पेस पे एक पॉइंट डिफाइंड है, ठीक है, उस पॉइंट की एक प्रोबेबिलिटी डिफाइंड होगी बड़े आराम से, और उससे आप फाइंड कर सकते हैं कि वो पॉइंट कहाँ लाई करेगा, जैसे अभी हम आगे चल रहे हैं। अच्छा, so you know y1 that when we assume that s1 was sent, so you know y vector will be like this, and assuming that s1 was sent, so you know the s1 signal will be like this. And we have already seen that y1 and y2 are uncorrelated, which means they are independent. This you should remember that for Gaussian random variable, if you can show that 2 random Gaussian random variables, they are uncorrelated, as we have shown that en1 and 2 they were giving a 0. This means they are totally uncorrelated. And once you are able to show, then you can very well say that they are also independent. And once they are independent, then their distributions are just product of marginal distributions, or you can say f1 and y2 given s1. And you know this distribution, this we have already found. y1 given s1, this means the mean has shifted to s1 point, which was under root eb. So mean, the distribution fy1 shifts to this mean, new mean, and क्या कहते हैं उसको, and the variance is n0 by 2, and you know this comes out to be, you know, n0 2 and 2 sigma square 2 and 2 cancels, this becomes n0. This has already also been shown. This comes out to be like this. So you take this value. Similarly, you will write f y1 y2 given s2. Okay, so you will be comparing both of them, as you have just seen that we will use this equation fi given s2 f, and we'll just compare them. All these exponential terms here exponential terms will remain here, and you will add all the exponential terms. ठीक है, ठीक है ना, ये स्क्वायर की सारी टर्म आ जाएगी. This term will also be there, and this will this will be 1 over e plus, and then this will become plus y2 minus yb, this plus y2 minus eb, this will come from here. This was already there, and this value will be again plus 1 over e plus y1 square 1, and then it will go here. This will become plus, and you add all the exponential terms, take log natural on both the sides. So this will, all these terms will be added, and you know, log natural of e is 1, and that power goes with the multiplicand. Log natural e is 1, so you get all of this here, and this totally here. You pi naught, you know, they will cancel, and ps1 ps2 you know, ps2 divided by ps1, log natural of ps2 and ps1. And here you can also see this will be actually you know, n naught. So this will be actually you know, this term over n naught, then this n naught will come here, so you will get this term. And सबको समझ आ गया how do we get this huge and long mathematical term? So as I've told you, these problems are very, very important. So they always come in exam, and always you are asked to find the questions are always changed, but the basic structure is always the same. You have to find the all these things, the correlator, the you know, you might be asked to find the match filters and what is the output. First of all, you have some signals and you have to orthogonalize them. There's vector space representation, then you have to make their receivers, and then you have to show what you are receiving. From the receiving, you show what is the from the demodulated part, you go to the directed part, you say what are the distributions of the received signal. Then you apply the Bayes rule or the maximum likelihood, and then you find this equation. You have to solve this equation further, so you can do you can very well see that these square terms they will cancel. Y2 will go with this one, this will cancel with this one, and you will be actually this EB they will also cancel, you know, EB square, because this is minus and this is minus, this is plus. So you will be just left with two AB terms. So these terms will be finally coming out of this long calculation. If you don't understand any step, then we can dwell into these mathematical equations, but they are not that difficult. So here you can take this you know, common, this comes here. So you have driven here in equation form. This will also carry marks that how can you for a journal value of PS2 PS1, how can you decide whether S1 was sent or whether S2? So you can see, let us say this is this is we will see some for example, but just for sake of simplicity, let us say this is some term. So if y1 minus y2 is greater than this term, this means that S1 would have been sent. Else if this value, let us say, is less than this value, then you will say that S2 has been sent. All right. So first case is, let us say that PS1 and PS2 is equal. When they are equal, log natural of 1 is 0. So we get a 0 here. So y1 minus y2 is less than or equal, greater than or less than 0. Or you can say y1 is and y2 goes here like this. So you will have a straight line, y1 is equal to y2, or that will be the you know boundary between these two regions. Yes, so you can also drive this threshold. This was derivation. So many times you are asked, and you definitely will be asked, that to, you mathematically solve the boundary condition. And but sometimes they say, all right, you don't have to write the equation, you can just draw it. Okay, so how can you draw this? So you can see that this was your S2 signal representation, this was your S1 signal representation, and this is the straight line y1 is equal to y2. All right, so if I just assume that these 2 points by some mathematical manipulations, that these 2 points are on this straight line, and we know that PS1 and PS2 they have the same probability, so this will become the same case as the antipodal case. If you remember in antipodal, what was happening? The 2 signals were under root EB and minus under root EB, they were just on a straight line. Okay, and the boundary and the threshold was exactly in the middle. So if I say, all right, these points, they are orthogonal points, but or orthogonal vector representation, but I can assume that they are on this straight line, and the boundary will be exactly in between. And this time will be y1 is equal to y2, as we have just driven previously, that y1 minus y2 less than or equal to, greater than equal is equal to 0. So y1 is equal to y2. This is the boundary for boundary of threshold or demarcation. If a point lies here, then this means that y2 will be greater as compared to corresponding value of y1. So you will say that S2%. If a point lies here, okay, then you can very well see that y1 will be greater than y2, and hence we can say that S1 was sent. So you can also draw the boundary condition by inspection, but it all depends on the question how it is asked. If they say, all right, drive, then you have to drive. If they say, all right, just find by inspection, then you can do it by inspection. So normally what happens that that you are told to drive mathematically, and then you are say asked to plot it on the 2-dimensional space, the boundaries. So you can do that. Otherwise, if you are asked by inspection, you can also draw it by inspection. हाँ जी, ये समझ आ रहा है कि मैंने आप लोगों को समझाया है किस तरह से इसको मैंने एंटीपोडल बना के स्ट्रेट लाइन करके इसको फिर हाफ में डिवाइड किया. हाँ जी, फायजा कंवल साहब, कैन यू अंडरस्टैंड?
जी सर, समझ आ गई.
चलिए, थैंक यू. All right, let's go further. Achha, now, yes, this was our inspection, but how can we do it mathematically? So he says that let y1 minus y2 is equal to z. All right, we know y1 and y2, they are just the outputs of my correlators, or you can say, let us say, if you have a match filter, of my match filter corresponding to correlating or match filtering with psi1 and psi2 of the match filtering or correlating psi1 and psi2 with the received signal. All right, so I say I define a new variable which is y1 minus y2 is equal to z. So yes, y1 and y2, they were actually coming out on an orthogonal subspace, okay, from psi1 and psi2, but I just take their values and say that their value is equal to you can say a new random variable which is equal to z. So actually what has had to happen, okay, you had these 2 random values which were actually on different orthonormal vectors, but you just took the values and you are just finding their differences. So you can very well see if y1 is greater, then what will be the value of z? Z will be positive. Okay, and you will say that yes, my point is towards S1, and hence S1 was sent. And if if z is negative, this means y2 is greater, then you can very well say that yes, S2 was sent. All right, so your detection problem by this substitution, okay, has again been transformed into a single variable. Now you are just deciding on a single variable z. Yeah. And actually we are not doing this by ourselves. We have just seen that after all that vector representation and after all that calculation, the boundary condition is just dependent, or your decision or your detection is just based on the values of y1 and y2. So why not make a simple variable which just gives us information that the y1 is greater, y2 is greater. So we just that on that two-dimensional representation, I have converted my problem in a one-dimensional space corresponding to z. ठीक है, यही इसमें सारा लिखा हुआ है. I hope you have understood this. अच्छा, ये मैं आपसे थोड़ा पूछना चाहता हूँ, शायद चूँकि स्टूडेंट्स कंफ्यूज भी रहते हैं. ये देखिए इसमें क्या लिखा हुआ है, y minus y2 is equal to 0. He has shown as this line. And so this is a y1 minus y2 axis. All right. Okay, if you remember your little bit of your electromagnetics, you will appreciate this. It is just like, you know, r1 minus r2 vector. This straight line, you know, this was your r1. If I just say for sake of simplicity, just to make you understand, this is, you know, r2. Then if I say that I have a vector from 2 to 1, so that will be represented by r1 because, you know, this is r1, this is r2. So this will be okay, from the head to tail rule, this vector will go from r2, will end it at 1. And so you can, this vector plus this vector is equal to r1. So you can very well say that this vector will be just r1 minus r2 vector. All right, so this line is actually, you can see r1 minus r2 because you're going from r2 vector and coming up to r1. ठीक है, ये आप अगर थोड़ा सा उसको EMT में ले जाए तो शायद आपको उसका रियलाइज भी हो जाए, वेक्टर रिप्रेजेंटेशन जो वहाँ आपने दी वो एग्जैक्टली यहाँ पे भी मैप हो जाती है. ऑलराइट, लेट्स गो फर्दर. So this we have actually done previously also. Now the problem has been simplified. You don't have to do your calculations in a two-dimensional space because of the transformation. You can do all your calculations on a single space corresponding to z. All right, and so you can apply all your mathematics of antipodal signaling to this problem. Once your PS1 and PS2 are equal, so you exactly take the same equation, but there, you know, we had y. Now this will be z. All right. And same equation, if you just compare this with binary antipodal, same equation there, same, but there it was y because already you had a single output, but here it is z. And you can see that y1 and y2, they are Gaussian. So z, which is, you know, y1 minus y2, this will definitely be also a Gaussian. You know, so addition and subtractions or any linear combination of random variable is also a Gaussian random variable is also a Gaussian random variable. All right. So let us try to find the mean of z. All right. So mean of z comes out to be under root EB. I think we should have done some steps here. So those steps are actually missing. So I will try to explain this. So it is y1 minus y2. But what is y1 and what is y2? So we have already seen, given that S1 was sent. So if you just go back here, so we saw that this was your y1 and this was your y2. So y1 minus y2 will be this value minus this value, and if you take the mean of y1 minus y2, ये अब स्केलर वैल्यू होगी ना, So mean of this is a deterministic value. This will come out of E. E of n1 is 0 minus E of n2 is also 0. If both 0, you will just get under root EB. Alright, that is why its mean is under root EB. अरे समझ आ रहा सारों को? क्या नाम है इनका? किससे पूछें आज? और बंदा नहीं? हाँ जी, हाफिज मोहम्मद उमर साहब. Are you understanding how come the mean is under root EB? हाँ जी हाफिज साहब, समझ आ रहा है?
Yes, sir.
समझ आया. चलो, वेरी गुड. थैंक यू वेरी मच. अच्छा, लेट अस गो फर्दर. अच्छा, now sigma of this is the mean, and sigma of z square is n naught. Now you will say, sir, how it comes? Again, follow the basis. Once you follow the basis, everything is very easy. All right. Again, I will try to make you understand. So I have not made the notes because I think they were easy, but still, if you require any, these calculations are not clear, then the next lecture I will also show its calculations. It's not difficult. So you know it is y1 minus y2, okay, and the mean is under root EB. So I will say y1 minus y2 is under root EB plus this minus the mean, but the mean is also under root EB. So, you know, this minus mean, you know, this EB cancels, okay, and you will be left with n1 minus n2. All right. So all right, so this will be E of n1 minus n2 whole square. समझ आ रहा है? Variance, how do we define the variance? Variance is expectation of the random variable minus the mean whole square. All right. I think I might have to end the lecture here because all right. So I try to end the lecture as soon as possible because I think they are calling me. So let us try to do it as much as possible. So what we were doing here, so we were trying to find its variance. All right. So its variance will be this random variable y minus y2 minus the mean. So this EB cancels and you get n1 minus n2. So you have E of n1 minus n2 square. And then you know n1 minus n2 square is n1 square plus n2 square minus 2 n1 n2, and you know that n1 and 2 they are uncorrelated, so this goes 0. So you will just remain with n1 square plus n2 square, and E of n1 square is already known. It is n naught by 2. E of n2 square is already known. It is n naught by 2 because their variances were n naught by 2 and n naught by 2 n naught by 2 they add, and you will get n naught. Are you understanding how do we got sigma z square as n naught? हाँ समाज में से समझ आ गया आपको n naught कैसे आया?
जी sir.
Very good. So once you know there is a Gaussian random variable, mean is this, variance is this, you can very well write its distribution. All right, this is all. So once you know the distribution, now everything you just have to put the values. Infinity to 0, 0 to infinity, fz, the random variable is here. So this means probability of z less than 0 because you are saying from infinity to 0, and this is probability of z greater than, yes, you can write like this also. So if yes, if p1 and ps2 are equal, they are same, so they become the same random variable, but their values are same. And p0, probability of pz less than 0 and pz greater than 0, they can be easily determined. And following the book, pz less than 0 and pz greater than 0, they will have for any Gaussian distribution, it is symmetric with respect to its negative and positive halves, so that is also the same, and hence you can add these two terms and they are symmetry, that they are half will add, and this will become 1. So 1 pz less than 0 or pz, both are same, so we take pz less than 0, this is just equal to this, ps1 and ps2 they are also same, and pz less than 0 is minus to 0. So before you write the Q function, remember that you have to convert this into a standard Gaussian distribution, then you can put in the Q function. Right. So same thing here as you've done previously. You write that try to make it normal, a standard Gaussian random variable with one, with 2 x square over 2 with one mean, and all that can be done by simple substitution rules. This you have said many times now, so no need to repeat. The limits will definitely change, and you will get here you can get this, but you can also see this is also from minus infinity to this, but you can also write this to be from integral plus integral EBO and not to infinity, because the area under the curve from infinity to negative number is equal to the area under the curve from the positive to the infinity. Then you can very well write this as this will come here, this will come here, both will become positive, and you can very well write this at q of under root EB over n naught. हाँ जी, समझ आ रहा है सारों को यहाँ तक? सलमान साहब, ये समझ आ गया कैसे आया? Should I dwell into this substitution? चलें, very good. So I think yeah, चलें इसको और कर लें थोड़ा सा. चलें इसको खत्म ही करते, 5 मिनट और लगा देते हैं. The rest of the time, if you are not able to do, we will cover in the next lecture. So what is the final note? End the lecture at this point. Actually, this is we always have studied thumb rules along with mathematical derivations of probability of error. There are also always some thumb rules, okay, where you can just apply, and rather than going through all those calculations, you can just say, all right, probability of error for this scheme will be as follows. Okay, so similarly there are thumb rules here also, and one of those thumb rules there, it represents the probability of error in terms of the distance between the 2 points on the vector representation of the signal with respect to orthonormal vectors. So yes, this is the right solution, as you've just seen, that probability of error is under root EB over n naught. But can we also write this in terms of its its vector representation? So what is the distance between these 2 points? The distance between these 2 points, this is just the Pythagoras theorem. This is the hypotenuse. This is the this is the base. This is the perpendicular. So square of this becomes 2EB, under root 2EB. This becomes the distance between these 2 points. All right. So I can also write my error as the distance. अच्छा, इन्होंने इस तरह से लिखा है half of the distance divided by under root n naught by 2, which is the variance of the noise in a single dimension. So you can also write it like this, but normally we write this as q of d, the distance comes here, divided by 2 into under root n naught by 2. All right, where n naught by 2 is the noise in each of the orthonormal directions, and it becomes 2 under root n naught by 2. D is the distance which comes above. So he has written 2 with the numerator, so it is also fine, no problem. But this is a general thumb rule. So you just put the distance between the two constellation points and you will get the probability of error. All right, this is also the right method of derivation, but instead of going through this long process, you can also write it like this, because if I put d is equal to under root 2 EB, all right, so you can say that this will become under root EB, and this will become under root 2. So under root 2 will cancel with this under root with this 2. This will become 1 over under root 2, and then this 1 over under root 2 and this 1 over 2, they will both cancel, and you will finally get EB over n naught, the same EB over n naught that you have driven here. So it is just a thumbs rule. Many times you might be asked, all right, without derivation, just give me the probability of error. So seeing the constellation diagram, you just find its distance and just put in this equation and you will get the probability of error. This is for that purpose. अरे क्या नाम किसी और से पूछते थे 144 नहीं आया ना. अरे ये वो कहाँ गई. अच्छा, हाँ जी सलमान साहब, ये समझ आ गया आपको जो मैंने ये थंब रूल बताया आपको?
जी सर.
थंब, अच्छा माशाल्लाह, वेरी गुड वेरी गुड. सो let's apply thumb rule again at some other scheme. So let us say antipodal. In antipodal, what is the distance? Distance is d is equal to 2 times under root EB, because this is EB here and EB here. This will be 2 under root EB, and you can also subtract the distance and you can very well check this will be 2 into under root EB. Put this here in this equation. 2 into under root EB, you can see that 2 cancels, becomes under root EB over n naught by 2, and this 2 and the denominator, in the numerator from the denominator this will go 2 EB, and 2 EB over n naught is the probability of error for antipodal scheme. And I think this we have already driven also. हमने उसकी भी नहीं देखी, उसकी निकाली भी हमने. This is by exactly by calculation, by following all the steps, and this is by inspection, or by thumbs rule, टोटका कह लें आप. Right? I hope you have understood till this point. So I will end the lecture here, and I'm very well, I know that we have 12 minutes left, but inshallah you will cover that in subsequent classes, so that there is we are with the lectures. If you have any question, you can ask before I end the lecture. I'm sorry for the recording. Some recording was missed, but I hope you won't need that recording. You can understand by yourself with the notes. But if there is some problem, you can always ask the questions. So I'm ending the recording also. Any questions? All right, no questions. Stop.